Alright, what's up guys, it's your boy Andy and we are starting the coding interview season as I promised. I'm going to be your mentor because I'm preparing for these coding interviews and I will take you along my journey. You will see what problems do I solve, how do I solve them, how I think about them. As probably some of you know me, I am that awesome teacher that at some moment of time was doing Code Forces rounds and I was explaining them and you really enjoyed my way of thinking about things and explaining my thought process. This is what you're going to do now, but for coding interviews, because I'm going to do some of them for fun. Maybe I get an offer, maybe not. I'll let you know. So yeah, basically an introduction. I'm Andy, ex-competitive programmer. Been teaching competitive programming for like 7 or 8 years now. I had a lot of successful students and I'm now the co-founder of Algo Academy, which is the best platform online to teach, to learn how to write code and how to ace your coding interviews and more in the future. So if you really like the way I explain things, if you really like these videos, make sure to leave it a like right now. Make sure to subscribe, hit that notification bell button. And yeah, if you think I'm the awesome teacher, I'm the most amazing teacher on the planet, you definitely should check out Algo Academy because all the videos are like this one, the same way of teaching, but a lot more time put into them. So without further ado, let's start. I started with Leetcode and I started from yesterday. I started practicing yesterday, although I didn't post anything. I'm sorry for that, but I wasn't feeling too well and I had a lot of business meetings for Algo Academy. So I really hadn't time to do that. But now we are going to see what I solved yesterday. And what's amazing about this series is that I already solved the problems, but now I come with a fresher vision, a fresher mind on them. You'll see me again thinking about them, and you will also see me writing again code for them. And this time I'm going to write the code after I've already got accepted, but then I've had some really nice insights from Mircea, which is the coding master. Mircea writes the most amazing code I've ever seen. It's the sexiest, most performant, cleanest and most quality code that I've ever seen. And you will see me how I approach things now with his advices and how I will progress and write better and better code for my coding interviews. So again, without further ado, let's jump into some things that I've done. So as you can see, I have this Amazon phone interview here from a year ago, probably was preparing for my Amazon interviews. Then I have this 4, which I made a day ago, and this one today. So we are going to see, let's see the most pretty problems and the problems that bring you more value, the most value, and we are going to solve them. So here, 458, not bad, right? But not good either. So it's probably not a past interview. So again, I'm not perfect. I'm Andy, but I'm not a god. And let's see. These problems were really amazing. Course schedule and course schedule 2 are the same problem, just that course schedule 2 is a little bit more complicated and binary tree maximum path sum is also really good. So what I want to do is show you how I thought about these problems and then we will code them together again. But this time in a better fashion. So we will start from course schedule 2, right? There are a total of n courses you have to take labeled from 0 to n-1. Okay, some courses may have prerequisites. For example, if prerequisites of I equals the pair A of I, B and B of I, this means that you must take the course B of I before the course A of I. Given the total number of courses, num courses, and the list of prerequisites pairs, return the ordering of courses you should take to finish all courses. If there are many valid answers, return any of them. If it is impossible, return an empty array. Cool. So, one thing I should probably do is make this a full screen. Maybe even zoom a little bit. Yeah, I think that's all right. Okay, so we have courses and we have basically prerequisites. A course should take should be done only after all those courses that it depends on are done, right? So let's see an example, right? For example, if the number of courses here is 2 and we have 1 and 0, this means that we should only do the course labeled with 1 after we do the one labeled with 0. So the order is 0, 1, and it's possible, right? Now we have this one, 1, 0, 2, 0, 3, 1, 3, 2. Okay, if we check this order, 0, 2, 1, 3, it's definitely right. Because first prerequisite, 1 should be after 0. It is. 2 should be after 0 in the order. It is. 3 should be after 1. It is. 3 should be after 2. It is. Right? Cool. So, how I thought about this. If you have a little bit of experience, it is pretty intuitive that on the problems that you have these prerequisites, these relations, like one thing depends on another, we are talking about a graph. This is what a graph does, basically, right? So the graph, like those elements, which in this problem are courses, are the nodes. And the relation between them could be prerequisites, could be maybe they are brothers, maybe they are friends on Facebook or something like that, are the edges. So we are talking about a graph. And we are talking about an ordered graph, right? Because we know that course A should be done only after course B was done. So I can have an age from A to B, which means that, all right, A depends directly on B. Let's take this example. Let's take the second one. And of course, I'm going to use my amazing Photoshop blackboard. So let's say we have 4 courses, right? So we have 4 courses. We can write them 0, 1. Okay, I didn't write on this table for quite some time. So sorry for the awful handwriting. 1, 0, right? I have an age from 1 to 0. 1 that depends directly on 0, right? Then I can have an age 2 and 0. 2 and 0. 2 should be done only after 0 is done. Then 3, 1 and 3, 2. I can have this 3, 1, of course, and I have this 3, 2, of course. So I have this graph. Basically, the problem asks me for an order in which I should perform the courses. So an order of the nodes, basically. It will be a permutation of all the values from 0 to num courses minus 1. In this case, from 0 to 3. But what should happen is that whenever I have an age from a node to another, I know that this node where the age starts from should be placed after the node where the age goes to in that order, right? So for example, here, a valid order should be, let's think. Well, we have this node 0, which as you can see doesn't depend on anybody, right? So if it doesn't depend on anybody, it means that it shouldn't be placed after someone or something like that. So I can place it the first one. Then I have 1 which only depends on 0. So 1 should definitely be after 0. All right, it is. 3 should be after 1. It is. And 2 should be after 0. Oh, wait. 3 should be after 1 and 2 should be after 0. So I was wrong. What I should do here is have it 2 and then 3. All right, and all the prerequisites are complete, are done, they are valid. So basically what happens is that we have a directed graph. And if you have again some experience, there is a definition of this order. The order of the nodes, the permutation of the nodes, such that when we have an age from a node to another, the age, the node where the age starts from is definitely before the node where the age goes to. And this order is called topological sort, right? So if you haven't heard about this ever, you definitely want to check this out. This is the topological sort, right? So basically we are given a directed graph and all we need to do is find this topological sort. Well, how do we find the topological sort, you might ask me? Yeah, how do we do it? There are 2 options. We can do it iteratively or we can do it recursively. Iteratively, we'll keep it for another lesson because recursively it's, I think, the cleanest and most elegant. But also remember that we should return an empty array if it is impossible to finish all courses. So we need to take that into account. Where do you think, without knowing necessarily what is a topological sort, when do you think that it will be impossible to find a valid order? So we have nodes depending on each other. What if I have a cycle? So 0 should be placed after 1, which should be placed after 2, which should be placed after 0. I can't satisfy all of this. I really can't. Let's say 0 is the first one. All right? Okay. If 0 is the first one, 2 should be placed after 0. Okay. 1 should be placed after 2. Okay. But I have this one. 0 should be placed after 1, which doesn't happen. So, the topological sort is only possible when this graph is not cyclic. So it doesn't have any cycle. So basically the problem asks me to do this. You are given a directed graph. If it has any cycles, return false. If it doesn't have any cycles, return me the topological sort. And that's it, right? So, because you don't have a lot of time to get into detail and prove what is the algorithm for the topological sort, I am going to explain very briefly, and then we are going to start coding, because this is how you get the most value. And if you want to learn it in depth, I really suggest you to look on Wikipedia or something. You will find a lot of great articles. So yeah, basically the thing with topological sort is the following one. If I have a node, let's call it node, right? And this node, of course, has edges to some other nodes. So node, 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 node. The thing is that in the topological sort, this node should be placed after its neighbors. So we need to have these neighbors in the topological sort added, and then we add the node. So we can do a DFS, a recursive approach, just have a DFS. And whenever we are inside node, right, which is the current node, we call DFS for every neighbor. Of course, if we find any cycle, we are done. And after we call DFS for every neighbor, we suppose that, all right, the DFS calls are finished, everything is fine, those nodes and their neighbors and so on and so forth are pushed into the topological sort. So after I do the DFS on those sons, I can add into my topological sort, just a name, I can add, push back my node, right? So this is basically the principle. You do a DFS, which is recursively. You process, you call DFS for the neighbors. After that, you make sure you push the node into the topological sort. And that's it. Now, in order to check if you have a cycle in a DFS, this is kind of easier, but all you basically need to do is basically when you are in this DFS, in some call, so you are in DFS of node, let's say, right? So this is the current node. How did you get here? You basically came from another node, came from another node, came from another node, and so on and so forth, right? You might not see this. I might have the face there. So let me make sure that you see this. So yeah, let's say this is node, right? You might came from another node, which came from another node, which came from another node where, and so on and so forth. And from this node, let's say that you have started the DFS call. So you apply DFS of this node and you came all the way through here. Basically, all you need to do in order to see if you have a cycle is that at some point in some node, if you have a back edge, so an edge that returns back to a node that you visited, that you have on this recursive stack, right? So this is called the recursive stack. When you apply a recursive function over and over again, you have a recursive stack made of all those calls. If you are in the current call, DFS of node, and you see that node has an edge which returns to another node, which is part of the recursive stack, so you know it's basically an ancestor, then you have a cycle. And this is what we have to do. We have to make sure that we make a DFS. We visit each node only once. So we will have a vector of Boolean to make sure that we don't visit node so many times, because that's definitely not big O of n. If you visit the nodes like an unlimited number of times, you might have something like n crossed m, which is not great. And besides this vector is visited, we will need another vector which is currently visited, which only marks the nodes that are visited in this function call, right? Because you might have, let's say, you have this graph. So you have this suns, sun, 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 then you have these suns, then you have these suns, and so on and so forth, right? Basically what happens is that you might start the DFS. Let's say the first DFS call that you do is this one. So you call DFS first on this node, and you go and visit all these nodes, right? Well, that's okay. Then you might call DFS from this node, right? So we don't necessarily know that we will call DFS from the parent node all the time first. No, we might call it from here and then from this node, which is an ancestor. So we have to make sure that when we call it from here the second time, when we try to call it from here, we don't call it again because we will visit again all these nodes. And this is a brute force approach. So that's why we have is visited. And also we need to know, okay, so let's say these nodes are visited. I'm not going to visit them again. That's cool. But also I need to know which nodes I'm visiting at this call. So this is why I will have two vectors. Is visited if it has been ever visited from any DFS call, and currently visited if it is visited from this current call. And this is what I need to check if it has a cycle or not. So enough talking. Again, check some articles on Wikipedia and stuff like that if you want to see more about the topological sort. And I think we will get into coding the problem. So let's do this. Let me, from OBS, I can move my face here so you can see better. All right. And what I also want to do is have this graphic tablet, because I don't have that many USB. This is kind of what sucks. I think I need an adapter or something. I don't have so many USB ports, so I need to switch between the tablet and the keyboard because I don't like the laptop keyboard. So yeah, I think we should do this. Okay, so I have this function, right? Find order, num courses, and prerequisites. Cool. First of all, I need to make the graph, right? We definitely need to make the graph. In prerequisites, we have pairs of integers, so A and B. So the edges are from A to B. Cool. So what I can do is iterate through prerequisites. So for, let's say, auto edge in prerequisites. Okay, this is the edge of 0, edge of 1. I need to push it as the edge, right? So first of all, I need a vector which will be basically the adjacent list of the nodes, right? So I need a vector of integers, which I can say it's going to be edges. And what size will it have? It would be of num courses. Yeah, and each one is initially empty, right? So for each node, an empty list of neighbors. Now, for each edge in these prerequisites, what I can do is edge of 0. Okay, edges of 0. I can do a pushback to edge of 1. Okay, so it's directed. We don't do the reverse operation. Cool. So it looks like I have the edges. Perfect. After I do this, I will need to call the DFS. So basically what I'll do is that I need that for each node. So I have to try out each node, some num courses I++. From each node, I will try to apply that recursive function, which is the DFS, right? Now, I don't want to call the function DFS. I think I can call it topological sort. So I will definitely need a function of void topological sort, which will definitely have here in the call the current node. And think about this. I'm going to need the is visited. I'm going to need the currently visited. I'm going to need a lot of vectors. One way to do this is, yes, I can declare here each and every one of them. And if I do that, I should pass into this function a lot of arguments. Is visited, currently visited, ages. I also need to pass ages and stuff like that, which I don't really like. So what I want to do here is inside the class, have those globally, right? So first of all, in order to not pass ages every time into the topological sort function, because I need to access it from there, what I can do is I can say, let's declare ages here in the class. And in this function, I can have ages to be equal to vector of int. I can have edges, yeah, to be equal to vector of, yeah, num courses and vector. I think that's okay. Yeah, yeah, that should be right. Okay. Then, what I still want to do is to have is visited if it has ever been visited. So vector of bool is visited. And currently visited, I also need to know if it has been currently visited, right? So currently visited in this recursive call. Right. Now, this is visited. This is visited is going to be vector of boolean. And what's its size? Of course, num courses. And initially, all of them are false. And currently visited, this is exactly the same thing. Currently visited will definitely start as num courses and false. All right. And now I have those globally. And now for each node from 0 to num courses minus 1, I need to apply the topological sort. So what I like to do is, first of all, I have to check if it hasn't been visited. So if not is visited of I, if this hasn't been visited, what I want to do is call the topological sort. All right, this topological sort will give me that order. But we have one more thing. First of all, we also need to know if we have a cycle or not. How do we know it? Well, we find this out inside the recursive function, so inside topological sort. So I'm gonna need this topological sort function to return a boolean, in fact. And I will have bool topological sort. And let's write as a comment. This one will return false if we have found a cycle in the graph. So if this is false, it's not successful and we don't have any order. If this is always true, we don't have any cycle, so we have our order of nodes. So if this is not visited, okay, I will be able to call topological sort. Okay. And inside topological sort, I still need to get my nodes in the right order. So I need a vector to keep those nodes right from the answer. What I can do, of course, is make this vector also in the class. So I can have vector of int and I can have sorted nodes. So topologically sorted nodes, right? This is the vector sorted nodes. And yeah, this is fine. If the node I is not visited, we should call topological sort of I. Okay. And we should be very careful, because if this returns false, then we have found a cycle in the graph. And this is not good. So what I want to do here is check if topological sort, oops, that's not, okay. Check if topological sort is false. If topological sort is false, then we have a cycle. And if we have a cycle, remember, we need to return the empty vector. So if this is false, then we return the empty vector. If this is not false, then everything is fine and we should continue. In the end, if we haven't returned false, then we will return the final sorted nodes vector. This is awesome. Now, let's get back into the topological sort function. This one, we are in node, right? Cool. So, when we are in node, we have to mark this node first of all as visited. So, is visited of node equals true. Then currently, also this is currently visited in this call of node equals true. Then I have to go to my neighbors, so to my next node. So for, I will have int, I can have next node, of course, in edges of node. So you see, now I need to access these edges. How can I do this? Either from this class or from this argument. But if I did it from the argument, I would have a lot of arguments and the function would just be ugly, not readable. So this is something that Mircea definitely, so it's not a fail, so it's not wrong to do that. It's definitely a good practice to do that, but the function becomes very messy. So you can do the class thing, just not to write a lot of code and yeah. Cool, so we have the next node. What we have to do for the next node is, first of all, check if we have a package. Because we are in node, if we have a package, then we have found a cycle. So when we go to next node, we might check if currently, actually what I would do here, even a better practice, when we have bools, make it is visited, is currently visited, just to make sure that, okay, so this is true or false. It's definitely a bool, there's no doubt about it, right? So is visited, is currently visited, sorted nodes, all right. So yeah, what I want to do here is currently visited of node equals true. If is currently visited of next node. So if this is currently visited, definitely this is a package. So definitely we have found a cycle, which is not good. So I can straight away return false. Found a cycle, it's not a success. Otherwise, this is not currently visited, so it's not a package. So that node might also be have been visited in another function call. If it's already been visited, I won't visit it again because it's slow, right? It's a brute force approach. So I need to make sure that it hasn't been visited. And then if it hasn't been visited, I can call topological sort of that node. And I have to make sure that that function call will not return false, right? So, first of all, if not is visited of next node, so this node hasn't been visited, I can call topological sort. One thing that I can do, and I initially did, is this one. If not is visited and topological sort of next node. So the node is not visited. I call topological sort. Topological sort returns true. And if it returns true, those nodes have also been pushed in the topological sort, which is great. So they are in the sorted nodes in the answer vector. If this happens, then everything is fine. But if it's not visited and we have found a cycle, I can return false. When I get out of this for loop, because I haven't exited the function, I haven't returned false anywhere, this means that I have performed every topological sort call that I needed. So my sons and their sons and so on are already in sorted nodes. And I need to push myself there. So sorted nodes dot push back of node. This is basically what I need to do. After I do that, of course, now I will return true because everything was fine. But before returning true, I am not currently visited. Currently visited of node becomes false, right? So I have been visited, I have tried my sons, but now that I go back in my parent, I'm not visited anymore. I need to find a backedge upwards, right? So yeah, basically this is how I think that I've implemented the function. All right. Yeah, we return true, cool. Back in the find order. So this is currently visited. Cool is visited, edges. All right. Yeah, I guess that should be, it. Let's try to run this. We might have errors, who knows? Okay, so for this first one is 0, 1, which is cool. Let's take another one. Let's take this 4 and 1, 0 and 2, 0 and 3, 1 and 3, 2, right? Let's run this code. Yeah, buddy. 0, 1, 2, 3, which is the same of 0, 2, 1, 3. Yeah, notice that the topological sort is not necessarily unique, right? So there might be multiple valid ones. Let's submit this. Let's see how I did. Yay, and it's been accepted. Nice, very nice. Very nice. All right. I don't know if you can see because I have my face, but yeah, it's basically a success. Cool. Now let's still take a look at the code because Mircea also did something amazing. So again, this code is very clean. It's 44 lines, which is amazing. But I could have made this topological sort function even more clearer. This is a thing that Mircea very good sees. And again, if you really like this code changes and how the code is going to change in a second, make sure you check out Academy. Mircea's got all those mind-blowing tutorials about how to write better code. Definitely check them out. So yeah, this is very fine here. I don't have any problem with this. Let's say I could have done something a little bit maybe more nice here. So what you should know is that it is not such a good practice to have a lot of returns inside a function, right? So as you can see, I have a return here, I have a return here, and I also have a return here. I have 3 returns in this function. This is not quite a clean code and not very understandable, right? What I could have done instead, and let's think about this, is that instead of making all these returns, basically I return false exactly when I find a cycle. So all that I do is check if I have a cycle or not, right? So what I should have done instead is make a boolean has cycle, which is initially false. Has cycle will become true if I have found a cycle, right? And when I go to next node, okay, one thing that I can do, is that I can call topological sort of next node, no matter what. So if I call topological sort of next node, no matter what, and I want to see if this returns false. Because if this is false, I have found a cycle, right? So I can do has cycle or equals not topological sort of next node. So I call this no matter what. Yeah, I call this no matter what. I update the has cycle. What I have to do is return not has cycle, right? Because if has cycle is true, I return false. This is not right. Okay. And now what I need to do here, because as you can see, I don't check if the next node is visited anymore, which I did. I can check it here. I can check if is visited of node. So if this node, where I'm now, has already been visited, okay. There are 2 possible options. it has been visited from another function call or from this current function call. I only want to return false if it has been visited from this function call. So if this node, which has been visited in this function call, this means that this is a backage. So I will return false. Otherwise, everything is fine. So if the node was visited, I return is currently visited here. Great. That's fine. Now, if it hasn't been visited, I move on and update the has cycle with topological sort. And yeah, that should be it. Also here, because now I check at the beginning of the function if the node has been visited or not. And if it has been visited, I just return something. All I can do is get rid of this if. So I can call topological sort of I. If it is false, I return this. Otherwise, it means that everything was fine. All right, cool. Let's try to run this code. Okay, let's submit it. Okay, and this was also a success. All right, so this is definitely something very tricky, right? Very fine. But there are these kind of details which really make the difference between you and another candidate. So, all right, you would have been done great on this coding interview without doing those changes, right? So now we have 2 returns inside the topological sort function instead of 3, which we had earlier. 3 was fine. So you would definitely have been done great. But this fine line is something amazing. So if you really tell the interviewer with the time that you have, after you implement the function, let's say you implement it not perfect from the start, but if you have a couple more minutes, you can ask him, all right, can I have a couple more minutes because I really want to make some design change to this function to make it cleaner and more readable. So trust me, if you do that, and if you are able to successfully do this, you will definitely be number 1 on his top list, because no one does this. No one does this on an interview. Everybody's like very stressed, very frustrated, very nervous to solve the problem right, to have enough time to code it fast and stuff like that. But no one says, you know what, if you can give me 2 more minutes, I can make this function very clean and very understandable. And you say, all right, I have 3 returns. That's not quite a good practice. What I want basically to do is see if I have a cycle. So let's have a variable. Let's go to each next node, call topological sort, update the has cycle, which I only return it in the end, so I don't have to return false on some cases and then true at final, and add these nodes. Yeah, right, cool. So this is the first problem that I had for you, and I also have done in that simulation. And the next one that we should do is this one. So binary tree maximum path sum. I'll take a break and come back to you later.